let's work through this test here. So this is a probability test, which again will make up about half of the next test that you guys take, and the other half will be the chapter that we're currently working on. So, event A, you live in Michigan. Event B, you live in the United States. Disjoint means that they cannot happen at the same time. You can live in Michigan and the United States at the same time, so they are not disjoints. A and B complements, that would be like A and B are the only two things that are possible. They fill up 100% of your Venn diagram. That's not true, because there's a huge overlap between Michigan and the United States. So no, they are not complements. Independent or dependent. Well, if I told you that you lived in, that would certainly change the probability that you live in the United States. It would make it 100%. So when knowing one thing makes the other thing more or less likely, that means that the events are dependent. All right, 4, 5, 6, 7, 8, 4, 5, 6, 7 here are all related. So A is 0.4, B is 0.7, A and B are independent. So independent, when two things are independent and you're asked and, you just multiply them together. So 0.4 times 0.7 is 0.28. When you're asked or, add the two events together and then subtract the overlap. So that is 0.82. And then A given B, well, there's two ways you could do this. One is you can go ahead and use that formula. So the probability of A and B is 0.28. We know that from number 4. The probability of B is 0.7 from the problem. If I divide those, I get 0.4. The reason I get 0.4 is because if these are independent, that means that knowing B is true doesn't make A any more or less likely. And it was 0.4 to begin with. This is like, there's a 40% chance it rains, and there's a 70% chance that I tie my shoes today. So this is saying, what's the probability it rains if I tie my shoes today? And whether it rains or not has nothing to do with whether I tie my shoes, so that's still going to stay 0.4. Are these mutually exclusive? So a couple ways to get at this too. All mutually exclusive events are dependent. And I told you these are independent, so that cannot be true. Another way is if you thought about a Venn diagram here, like if you constructed one based on what we have so far, this is 0.28. This would be like 0.12 because these have to add up to 0.4. This would be 0.42 because these have to add up to 0.7. And then if you're thinking through this, if you add up these three numbers, you'll actually get that answer there too. But there's overlap. So if as soon as there's overlap, the two events are not mutually exclusive. What's the probability of getting at least two tails when flipping 3 coins? So make a little tree diagram. And there are 8 possible outcomes. How many of them have at least 2 tails? Well, that one does. That one does, that one does, and that one does. So 4 out of the 8, or 1 out of 2, or 0.5. Number 10. So I've got the probability of rain on Saturday and Sunday. So I know P of Sat and Sun is 0.35. The probability of rain on Saturday is 0.55. The probability of rain on Sunday is 0.4. Found the probability of rain Saturday or Sunday. So or means you add up the two things and then you subtract the overlap. So in this case, that would be 0.55 plus 0.35 minus 0.4, which comes out to, 0.55 plus 0.4 minus 0.35. So A, I'm looking at like Saturday is the A, Sunday is the B, and then the overlap is there. 11 is the same formula, but I kind of flipped it on you. This one's a little tougher. So the probability of Monday or Tuesday It's the probability of Monday plus the probability of Tuesday minus the probability of Monday and Tuesday. So I gave you this, which you're not used to. So that's 0.4. The probability of Monday is 0.25. The probability of Tuesday is 0.35. And then this is like your x. You're looking for this variable. So you end up with like 0.4 equals 0.6 minus x. So this must be 0.2 to make that work out. All right, for this table, female if given Republican. So if I know that the person's Republican, I'm looking right there. I don't care about the other two columns. So there are 130 total Republicans, 50 of them are female. Male or Democrat. So you've got to find male, Democrat, and then subtract the overlap. So there are 110 males, there are 90 Democrats, but then this group of 30 was in there twice, so you have to subtract out one of those. So 110 plus 90 is 200, minus 30, so it's 170 out of 220. And then our gender and political party independent. Well, if they were independent, you would have the same ratios all over the place. So 30 out of 110 males are Democrats. If these two things were independent, 30 out of 110 females would also be Democrats. Or maybe 60 out of 120, but it'd have to be the same proportion. And that is not true here. So that is no. True, false. All mutually exclusive events are also complements. That is false. An example of that would be, you get an A in a class, or an A in this class, or you get a B in this class. Those are mutually exclusive. They cannot happen at the same time. But complements means that they're the only two possibilities. And they're not, because you could get a C, you could get a D, or hopefully you don't fail. 16, all complements are also mutually exclusive. That's true. The definition of complement is two events that are mutually exclusive, and they're the only two things that could happen. So, to qualify to be a complement, you have to be mutually exclusive first. That's one of these scenarios. Where this up here is more like A, B, and then you've got all this other space, other things could happen. If a family has two children, the complement of boy, boy is girl, girl. So again, complements have to be the only two options. So if one of your options is boy, boy, the complement of that is all of these things combined, not just girl, girl. Like boy, boy, and girl, girl do not fill up the entire square. There are other possibilities. So that's false. Some of the probabilities in a distribution must add up to 1. So a probability distribution is like one of these guys. And these numbers do have to add up to 1 because they do have to represent 100% of the possibilities. If two events are complements, their probabilities must add up to 1. So complements are, these are complements up here. They have to be the only two things that can happen. One of those two things has to happen 100% of the time. Like heads or tails. Or you pass the class, you fail the class. That represents every possibility, so that is true. If two events are disjoint, the probabilities must add up to 1. That's false. So disjoint is more like the A and the is mutually exclusive. So getting an A in this class and getting a B in this class are disjoint, but the probabilities don't add up to 1 because they are not the only two possibilities. 19 through 21 here. So A, B, and C are all mutually exclusive. So I'm going to make a little Venn diagram. They do all add up to 1 too. So for 1 also. So A happens 0.4. B happens 0.2, C happens 0.4, and there's no overlap there because they're all mutually exclusive, so none of them can happen together. This would be like if the only 3 grades you could possibly get in this class were an A and a B and a C, and you couldn't get anything else, you couldn't get any two of them at the same time, and they were the only possibilities. So the probability of A or B, so when you're doing OR, you have to add up the two events and then subtract the overlap. So adding these two events will get 0.6, and subtracting the overlap is subtracting 0 because they cannot overlap. So this is just 0.6. Find the probability of B and C, so there's no overlap. So what's the probability you get a B in this class and a C in this class? 0. And then the probability of A given C, so that's like saying, what's the probability you get an A in this class if it's given that you got a C in this class? So like, if we know we're in this box, what's the probability we're also in this box? Is 0. Okay, 20 out of 100 males had blonde hair. So that's 20%. If gender and hair color are independent, that means gender makes no difference and that 20% of all females should have blonde hair also. So there's 100 male students, that means there's 200 female students, 20% of 200 is 40. 24, so the first thing I would do is fill in this. So this is like the probability distribution. The sum of the numbers has to add up to 1, so this has to be 0.2 to make that happen. And then, what's the probability of getting 15 points if you know you got at least 10? Well, if you know you got at least 10, that gets covered up and doesn't even count anymore. So now the total of your possibilities isn't 1 anymore, it's 0.9. And the probability of you getting 15 points is still 0.4. So that becomes 0.4 out of 0.9, or 4 out of 9, either way. Probability of getting a 5 if it's given that I got less than 20. So if I got less than 20, I covered those up. There's only 0.8 possible now. And then the probability of getting 5 is still 0.1. So that'd be 1 out of 8. Play twice. Each time is independent. So that means we can multiply. Find the probability of getting the same result both times. So the probability of getting a 5 and then another 5 is 0.1 times 0.1. The probability of getting a 10 and then another 10 is 0.3 times 0.3. 0.4 times 0.5. Or 0.4 times 0.4. And then 0.2 times 0.2. And it could be this, or this, or this, or this. And remember, or means add. And if I work all that out, I think it's 0.3, but I don't have the answer key in front of me, so let me just verify. Yeah. Expected number of points, so expected value is the probability times the outcome plus, and then you just keep doing that. So there's a 0.1 chance I get 5 points, a 0.3 chance I get 10 points, a 0.4 chance I get 15 points, and a 0.2 chance I get 20 points, and if you just throw that in your calculator, you get 13.5. 25. This is a tree one. This is a tougher one. So the first thing, there's a 20% chance, let's just say chance, of a flight being delayed because of icy weather. So icy weather, 20% chance. No icy weather, then has to be an 80% chance. If it's delayed because of ice, so up here, there's a 15% chance that there'll be an additional delay due to mechanical. Which means there's an 85% chance that there won't be a delay due to mechanical in that situation. If it's not delayed because of ice, there's an 8% chance that there will be a mechanical delay. Which means there's a 92% chance there's not a mechanical delay. And then they're saying find the probability that there are no delays. So the only one I really care about is this combination of branches. There was no ice delay and there was no mechanical delay. So you're just going to do 0.8 times 0.92. And some people could probably do that without making the tree. That's absolutely fine. But the tree can also be very helpful. So there it is. 26. So make a Venn diagram first. So I've got my 2 circles. So science here, English here. Start with the overlap. So 20% take both. 40% of seniors take a science class. So the science circle has to have 0.4 total. I've already got 0.2 there. So there's only 0.2 left to put there. The English circle has to be 0.5, but I've already used 0.2 of it, so there's only 0.3 left. And then the whole box has to add up to 1, so I've used 0.7, which means there's 0.3 on the outside. So the probability of science given English. So if we're in the English circle, how big is the English circle? It's 0.5. And then what part of that circle is also in the science circle is 0.2. So that comes out to 0.4. English given science is just the opposite. So if I know we're in the science circle, so now we've narrowed it down to 0.4. What's the probability we're also in the English circle is just this 0.2. So it's 0.2 out of 0.4, which is 0.5. And then our science and English independent, they actually are, because 40% of seniors take a science class. And then if I go down here, if I tell you that they took an English class, now what's the probability they took a science class? And it's still 0.4. So whether they took an English class or not didn't make it more or less likely they took a science class. It stayed the exact same, 40%, 0.4. So they are independent. Science or English, you're just going to add up all three of those numbers. That's 0.7, and then the neither is 0.3. And these two numbers, the or and the neither, should always add up to 1. And they do, so we're in good shape. Okay, the Frappies. So, for treatment plan 1, let's see. Treatment plan 1 is antibiotic A first. So there is a 60% chance that the child is just cured and we are just done. Or if that first treatment didn't work, which there is a 40% chance of, then we go to antibiotic B, which has a 90% chance. So there's a 60% chance. So there's two ways the child could get cured. Either the first antibiotic works, or, which means plus, the first antibiotic didn't work, and the second one did. Remember, and means multiply. So then this is 0.96. Treatment plan 2, same thing, just flip. So there's two ways that the child could get cured. There's a 90% chance that they're just cured the first time. They're just done. Or, the other way they could get cured is if the first plan didn't work, and the second one did. And that also comes out to 0.96. Expected cost for plan 1. So plan 1, there's a 60% chance that the first treatment worked. If that's the case, we paid $50 and we stopped. We're done. We don't have to pay anything else. But there's also a 40% chance that we have to pay a total of $120, because if the first doctor didn't work, we have to also go to the second one. We don't get a refund from the first one. So our expected cost here is $78. Treatment plan 2, there's a 90% chance that the first treatment of $70 works, and I'm done. There's a 10% chance that I end up having to see both doctors, and that means I will have paid $120. And this one comes out to $75. So they both have the same probability of curing the child, and this one's cheaper. So that's what you want to say in part C. I would recommend plan 2 for 2 reasons. Because it has the same probability of success of curing the child, and is cheaper. All right, now we got this disease, positive, negative, false positives, false negatives, this whole deal. So we start off with what percent of the population has the disease. So large-scale studies have shown that the disease occurs in about 3% of the population. So have disease is 0.03. No disease then must be 0.97. Well, if you have the disease, you might test positive or negative. And if you don't have the disease, you might test positive or negative. So let's find those numbers. So there's a positive result 4% of the time for people who do not have the disease. So positive test, do not have the disease, goes here. There's a negative result 1% of the time for people who do have the disease. So have the disease, negative result is 0.01. And then you know these two things, so they're complements. They have to add up to 100. So this is 0.96, and then the same thing there. This is 0.99. So part A is asking, what's the probability that a person selected at random would test positive? Well, we tested positive in that scenario and that scenario. So we multiply those numbers together, and then we add them up. So they had the disease and they tested positive is 0.0297. Remember, and means multiply. Or, which means add, they didn't have the disease and they tested positive. So that means multiply these two. So 0.0388. And if I add those up, I get 0.0685. And then what's the probability that a person who selected at random who does test positive, so it's given that they tested positive, does not have the disease? So the formula tells us to do probability of no disease and positive divided by the probability of positive. Well, no disease and positive is this number here. And positive is this answer here that we just had from part A. And if we divide those, we get 0.566. I believe that's it. So hopefully that helped. Please study it. Please ask me questions if I can help.